All right. I don't know if anybody has any questions. If you have any questions about today's exam, fluids, gases, make sure you ask because, like I said, I'm probably gonna finish this by seven something. Huh? It's not a lot. So that's that will be the topic of today. All right. Okay. So yesterday I started already introducing the concept of heat. And I have already mentioned that heat is transfer of energy from a hot to cold body. All right? Which is basically the temperature difference between them. I have already, or you already know this term, internal energy. It's going to be very useful in chapter 12 when we start talking about thermal processes like adiabatic, isobaric. We have gases where you introduce heat, then the gas can do work, and then you have a change on internal energy. Internal energy, as you know, is the one associated with the atoms and molecules. As you know, if you increase the temperature of a gas, the molecules or atoms are going to move faster. They increase their kinetic energy. The overall kinetic energy is the internal energy of the gas. For a monoatomic gas, it's 3/2 of nRT. That's the equation that we already introduced in chapter 10. We're going to expand on that later on, but this is important, all right? So focusing on heat, right? We have two units for heat. Yesterday I introduced the joule, of course, as energy, but you are probably more used to the idea of calorie. When you guys are burning calories by doing exercise, is because, and you are sweating, is because you are doing work. And what's work is change of energy, right? So the calorie is the energy necessary to raise the temperature of 1 gram of water by 1 degree Celsius. All right. And that is the conversion between calories and joules. Now, yesterday I introduced the concept of a specific heat. Right? So I said that you have this value C, which we know as the specific heat capacity. And this guy can be measured, well, you know, joules per kilogram Celsius. But if we're using calories, we can use calories per gram per Celsius. So then that 1 calorie, right, like it says in the book, is the energy necessary to change the temperature of 1 gram of any substance, particularly water, by 1 degree Celsius, right? So the specific heat capacity of water is equal to 1 calorie per gram per Celsius. Or in joules, the specific heat capacity of water is 4,186 joules per kilogram Celsius. So from there, we get that 1 calorie is with grams. 4,186 joules is with kilograms. So we divide by 1,000, that's 4.186 joules. That's where your conversion comes into place, right? So that's what this means. So then a specific heat or specific heat capacity is defined as the amount of heat divided by the mass times that change on temperature. And here is your equation for heat. Heat is labeled with the variable Q. All right. Why not H? Because H is enthalpy. Right? In chemistry, when you have energy, exothermic and endothermic reactions, you have absorption or releasing of energy. That is the variable H or delta H, right? Q is used for heat because we use calor, right? Or in Latin, is written with Q. So there you have it. Now the units for heat, because its energy is joules, mass in kilograms, temperature in Celsius. So we use joules, kilograms, Celsius most of the times for the units of a specific heat or specific heat capacity. Now you have a table here with some specific heat capacities in both joules, kilograms Celsius, and calorie gram Celsius. So for example, for aluminum, is 900 joules per kilogram Celsius. For water is 4,000. Water, it has the largest of all these substances, right? So what does that mean for water and aluminum? Any other metal like gold. Gold has a very low specific heat, or iron as well, right? It's 448. Gold is 129. That means that it's very easy to change the temperature of gold, right? Look at this example here. If you have a half of a kilogram of water and the change on temperature is 3 degrees Celsius, I think I mentioned this yesterday, right? The large specific heat capacity of water makes it that even though you don't have a lot of mass and the temperature change is just 3 degrees, the amount of energy is 6.28 thousand joules, right? If I were to change that into calories, so how do I change joules into calories? I just divide this number by 4.186. So it's about 1,500 calories. 1,500 calories what you burn in a day if you are physically active. All right. So imagine if you have the mass of a lake, which can be several tons of water, right? In mass. A ton is 1,000 kilograms, by the way. So then if you change it just by 2 degrees or 1 degree, it will be a lot, right? Like let's do the multiplication. If it's just 1.5 degrees Celsius times 4,186, and you have 10 tons, which is 10,000 kilograms. That's your amount of joules. In calories, it's 15 million calories. So it is something that we cannot just ignore, right? Especially if we're talking about largest amounts of water. However, if we do the same for aluminum, right? Let's do this example with aluminum, right? Instead of having a half of kilogram of water, I have a half kilo of aluminum. The specific heat of aluminum 900, and the change of temperature 3. So it's only 1,350 joules. In comparison with that, right? It's way less. And then if I divide this by 4.186, it's only 322 calories. It's what you burn in the gym in a treadmill. So, right, it's not a lot. And you know, half a kilogram of aluminum, half a kilo is the largest mass that you can use in a lab. You know those masses that you've been using for the experiments? That would be the largest mass, 500, and they are quite heavy, right? Half a kilo is, you know. So it's not a lot, but still, the specific heat makes a big difference. That's the idea. Then we have this to illustrate heat and internal energy. Can anybody explain what is this? What are the arrows showing you? There's a nice name for this. Think about how energy is transferred, how heat is transferred. what are the three ways heat is transferred from one body to another? Nobody knows? What will be this? What type of energy transfer is this? Is here. That is conduction. All right, when there is a direct contact between two bodies. This is what we know in physics as convection, which also happens when you cook. When you cook soup, right, or you're boiling water, you start seeing bubbles on the top, on the surface of the water. Those bubbles are not just on the surface, they are all over the liquid. You see, as heat rises, the cool liquid drops, goes down to the to the uh, to the ground, right, to the bottom. But then they get heat up because they are close to the stove, and then they rise up. That's what you see here. Hot air goes up, cool air goes down. It's the idea behind crawling during a fire, right? Why do people crawl when there's a fire? Because the cool air is actually going down. So it's easier to actually move instead of just standing without the hot air. Besides the smoke, of course. This phenomena is observed a lot in the beach because after long periods of radiation, which is the other form of energy transfer, so you have conduction, convection, and radiation, the hot surface in the around this time of the afternoon, hot air rises up and cool air drops, right? So this convection phenomena happens a lot in real life, and sometimes it's used to do, for example, hang gliding, right? Hang gliding is used by taking disadvantage of these columns of hot air rising up. That's why it has to be windy and warm. Like a day like today is a perfect day to do hang gliding or paragliding, all right? Or to fly a kite. So that is how heat is transferred from one medium to another. And that's basically help us understand heat, which is a form of energy transfer. But the best experiment to understand the usage or how heat is transferred from one body to another is the experiment of calorimetry, which many of you have done already. You can find animations online a lot. You can do it in physics or chemistry. See if I can find a link for this. There it is. There it is. So basically, you can choose any liquid, any mass, right? Well, it's really fantastic. It depends on the bibliography. Sometimes they round it 4.184, but it's actually 4.186. Again, it depends on the reference that you use. So I click here. What is the next? Okay. So let's say that I have water at 20 degrees Celsius, and then water 170 grams, and now it's at 90, so it's almost boiling. So you're transferring the cold water here, You close it and then you see the temperature change. So what's happening right now is that the cold water that was here was mixed with the hot water. You close the calorimeter and they are slowly reaching what we know as the temperature of equilibrium. Now, guys, be careful. I know some of you are wondering, but hey, the temperature is dropping a lot from 90 to 61.75. And that's not what I saw in the lab. Yes, you didn't see that in the lab because here we're mixing water and they both have the same specific heat. What you saw in the lab was this. Okay. Oh no, but this is, oh yeah. So like 90 and then next water. I think somewhere you had like 175, 20 is fine. And then there. So I introduced the hot metal here. That's what you did. And then the temperature is rising, but not by a lot. And here's just showing you when it reaches equilibrium. So almost 4 degrees. Okay, again, this shows probably the mistake in the lab, right? That you have to wait quite some time for these two bodies to reach equilibrium. But I remember that the mass that you guys had for this guy, I think it was about this, but some of you had more mass of water. Still, it should be raised by at least 3 degrees or 4 degrees. But if you compare it with a previous experiment that I ran, the temperature change is way lower. Why is that? Because the aluminum has a very low specific heat in comparison with water. So the aluminum can easily drop from 90 to 24 degrees Celsius, while water, because it has a high specific heat, it increases its temperature, but not by a lot. And now let's do something nice. Let's show you the math behind this experiment. So the idea with calorimetry is that the heat, which is Q, gained by a substance is equal or identical to the heat lost by the other substance when they reach equilibrium. So the way I like to solve this, and I show you already this before, is by drawing a line and by locating who is gaining the heat is the water, because the water was at 20 degrees Celsius. So this is at 20 degrees Celsius. This is H2O. And it increased, so I want to exaggerate it, to 24.07 degrees Celsius. So that's the Q gain, this section. That's that. Q loss was for the aluminum, which was at 90 degrees Celsius. So for the aluminum, it decreased from 90 to 24%. So they both reach this temperature of equilibrium. So then what's Q gain for water? Q gain is the mass of water, 175 grams. I'm going to use joules. So 0.175. The specific heat capacity of water and the change on temperature, this minus that, so let's do the math. 0.175 times 4186 times 4.07. So that's 2,981 point, yeah, 2,981. Let's round it like that. Let's leave it like that. Joules. Now, what's the Q lost? That's the one for aluminum. We should put here aluminum. The mass of aluminum was 50 grams, so 0.05 kilograms. The specific heat of aluminum, which is 900, and the change on temperature, 90 minus 24.7. 65.93. Well, I will check that out. Yeah. So now I do the math. Look at this. 2,966.85. So it's almost, well, it's just 200 this joules. So this is almost identical to this. That means that the amount of heat gain is basically the amount of heat loss. That's conservation of energy. There's some difference. Can somebody explain where the other 15, the other 15 joules are? Why there is a difference? Which is minimum, but why? There is a difference though.
Is it lost to the environment?
Very good. We are assuming that nothing is lost in the environment, but you already know from the experiment or from previous references, right? That even in a perfect calorimeter, there can be something lost in the environment, right? That experiment, by the way, online assumes that. So I remember during COVID, we used that for the calorimetry experiment. Because you can actually use it to find the specific heat capacity of unknown elements. Basically what you guys did in the lab. So yeah, a calorimeter is insulated, but there is always something lost. The other thing that you probably have realized is I didn't take into consideration the heat gain by the calorimeter. You see, when you have the calorimeter, right, with water first, the calorimeter and the water, they both are at equilibrium, 20 degrees Celsius. Now, in this case, this calorimeter seems to be not made of any specific material, so you can actually ignore it. But when you are doing this in real life, if you're using a calorimeter made of aluminum, you have to consider that both the water and the calorimeter, they both are gaining heat. And that makes a difference, for sure. All right. Which, by the way, that's the reason why also the temperature here increased by more than in your experiment, right? In the experiment, we assume, which is not wrong, but we have to consider the calorimeter. We cannot ignore it. All right. Any questions? So obviously, this will allow us to solve quite a few examples using unknown elements or even mixing substances and finding the temperature of equilibrium. However, we cannot ignore that there are phase changes. You see, what you are learning right now is that Q, the amount of heat, depends on the mass of the substance, the specific heat, and the change on temperature. So to have heat absorbed or released, there needs to be a change on temperature. But what about latent heat and phase change? You see, ice is melted and then it becomes water. And then eventually that water can evaporate. Right? When you boil it, it evaporates and it becomes gas. That is a phase change. So we call it latent heat. Latent heat is the idea that you can have energy absorbed, in this case by ice, and melt, and then it's melted into water. But when you are melting ice, you are not changing the temperature of ice. I know it sounds weird, but hear me out. Ice, if you go to your fridge right now, is at 0 degrees Celsius, well, approximately. If you remove it from the fridge, you dry it, and then you place it in water, it starts melting. But in the process of melting, the ice is not changing the temperature yet. The ice changes its temperature once it's melted and it's mixing and it starts mixing with water. The same if you are evaporating gas. If you are boiling water, but water is still liquid, you start seeing steam. That is a phase change. Now, the steam is still at 100 degrees. Once the water has totally evaporated into steam, you can keep raising the temperature of steam until in some cases you can make it become plasma, which are superheated gases. For example, the matter of stars, right? The sun or any other star are not glowing balls of gas, which I always correct students when I teach astronomy, right? That's an oversimplification. Stars are actually balls of plasma, which are superheated gases, very, very well conductors, all right, of electricity and heat. So the idea of latent heat is that you can introduce energy, or you can give energy to a body to produce a phase change. And you can see it better in this graph. So what do we have in this graph? We have ice. We have certain amount of ice, which we are changing by 30 degrees Celsius, so you have this amount of energy. In this graph is basically increasing the temperature of ice from negative 30 to 0. So the change on temperature is 30. 0 minus 30, 30. So that's here. The mass of ice is this, and this is the specific heat of ice, by the way. So there you have it. So you can visualize that by this line going up. But then you have this process. It says here ice plus water. So what's happening here? Here, as you can see in this graph, there is no change on temperature. The temperature is constant at 0 degrees. So this is your latent heat. Energy added, which is heat. Ice is melting and mixing with water. So all this ice is now melting, and I can find that the amount of heat to melt that ice is here. Is the mass of ice times this. What is this number? We call that the latent heat of fusion for water. This ice is water, just in solid state. So you have latent heat of fusions for different substances, and you also have latent heat of vaporization for different substances. All right. For water, and this is interesting, look how much energy you need to melt ice. This was the energy to increase the temperature of ice. The energy to melt the same mass of ice is this. It's way more. It's 5 times more. Why? Because of this factor. So latent heat is generally larger than your normal heat. And then once you melt all the ice into water, they both are water, so they mix. They reach the temperature of equilibrium at 0. And then you can keep increasing the temperature to 100. So 100 degrees, the specific heat of water and the mass of water. Now it's water. You change ice into water. So this is all the energy to basically boil water to get it to 100 degrees. But you haven't evaporated it yet. Boiling is not the same as evaporation, by the way, guys. Boiling is reaching 100 degrees. So you're boiling water. Evaporating water is when you change the water from liquid to gas. All right? So then we're looking at that process now. There. The same mass times the latent heat of vaporization is this process here, which is way more than this. Why? Because of the latent heat of vaporization. Once you evaporate all the water, you are in steam. And you can keep increasing the temperature, right? You go from 100 to 120. This is the latent heat of water in gaseous state, by the way. It's almost like the one in ice, but you know. So you can add all the energy for every process. Heating ice, melting ice, heating water, evaporating water, and heating steam. 1, 2, 3, 4, 5, and there you have it. All right. So that's the idea with, that's one of the main applications, right? So then now you know why it's so concerning when you have largest pieces of ice melting in the Arctic or sometimes even in the South Pole, in the Antarctic, right? Because look at the amount of energy you require for that to happen. And where is that energy coming from? It's obviously coming from the Earth itself. It can, well, the major source of energy is the sun. But have you guys ever heard about the greenhouse effect? Who can explain in simple words what's the greenhouse effect?
Is it like when the gases of the earth trap the heat from the sun
Yes,
in the earth's atmosphere?
very good. Exactly. Yeah. So what happens is that if they are trapping the heat or way more than it should, then the air is quote unquote warming up. And that's why the poles can increase their temperature faster and then melt faster. Faster rate. Like I said yesterday, it's still up to debate if it's an increase of greenhouse gases triggered by humans or as a natural increase, because we have had climate change events in the past, right? So it's nothing new, but is it being triggered or accelerated? That's the whole part of the discussion, right? And then if you look at planets like Venus, where it has a extreme running greenhouse effect, well, you have a planet that is basically harmful or not suitable for life because of the very large greenhouse effect. The temperatures of the planet, Venus, make it the hottest planet in the solar system, right? With acidic rain and sulfuric acid and all that, right? And then the lack, that's one of the extremes. The other extreme will be the lack of greenhouse gases. Where do we see that? We see that in Mars, right? You probably have heard, you probably have read that Mars, billions of years ago, had rivers, water, and we believe that there was some sort of life, maybe organic life, in Mars billions of years ago. And then exactly we don't know what happened, but the planet ended up dying. All the water on the surface dried, and then it went to the polar caps, right? So one of the reasons is the extinction of the atmosphere and its magnetic field, right? The magnetic field of the Earth is one of the factors to keep the atmosphere in place, right? And of course, the gravity and the tilt of the Earth and all that. But the lack of an atmosphere, the lack of greenhouse gases in Mars, makes it with large temperature fluctuations, right? It can be not warm, but it can be a little bit above 0 degrees Celsius in the day and really, really cold at night. We see the same in the moon. The lack of an atmosphere makes it for very large temperature fluctuations. The reason we don't have that in Earth is because of the greenhouse effect. Okay? And what are greenhouse gases? Carbon dioxide, carbon monoxide, and water vapor, among others. Okay. Any questions? All right. Let's start with something simple. Let's start by converting. All right, so you guys know how to convert, and then we can do some problems on calorimetry. So, how do you convert calories to kilocalories, right? Or joules, right? This one, if you have 3.50 times 10 to the 3 calories, kilocalories is basically 1,000 calories, so it will be 3.50, right? So you look at the answer, it's just 3.50 kilocalories, right? Now, if I want to convert this amount of calories into joules, like I said, you just divide 3.50, 3,500, we just divide by 4.186. And that's 836. Let's see how they run this. Oh, what happened here? Oh, my bad. I'm going from calories to joules. If you're going from calories to joules, you multiply. Because remember the conversion factor, right? 1 calorie is 4.186 joules. So if you're going from joules to calories, you divide. But if you are converting calories to joules, right, you are just going to multiply times 4.186. So that's the answer here. If I convert this into scientific notation, is 1.47 times 10 to the 4 joules. Okay. All right, so let's take a look at some examples on calorimetry. Let's start with this. It's asking you what mass of water at 25 degrees Celsius must be allowed to come to thermal equilibrium with 1.85 kilograms of aluminum, initially at 150, so that's very high, to lower the temperature of aluminum. Okay, so let me show you how to solve these problems, all right, using this method. So, so you are going to draw a number line, a line. And then you are going to locate water at 25 degrees Celsius. So water. You know how much. So you know the mass. And it's going to be mixed with 1.85 kilograms of aluminum at 150 degrees Celsius. So around here, this is aluminum, 1.85 kilograms, right? and it's gonna go to equilibrium at 65 degrees. So it's gonna raise, it's quite a lot. So it's probably not a lot of water. Why do I do this method? Because it's easy to visualize Q gain, Q lost. Q gain is equal, if we assume there is no loss in the surroundings, and that's what determines the problem, is equal to Q loss. So Q, remember, Q equals to NC delta T. Delta T, right? So that's what Q is. So the mass, you don't know. So mass of water, the specific heat of water, this number, I want to be honest with you guys, you should memorize it. Not because it's not going to be given, but it's a number like the density of water, right? That is a universal number. It's important that you guys know it. So this times this. Change on temperature, easy. 65 minus 25, 40. And then Q lost by this. So mass of aluminum, 1.85. Specific heat of aluminum, 900. If you don't remember, you can just go to the table. Aluminum, 900, right? So 900. And change on temperature, 150 minus 65 is 150. Wait, 50, 85, sorry, 85. All right, so my mass is this, right? Divided by this. All right. So let's see what mass of water was that. Yeah, not a lot. 0.84, yeah, 0.85 kilograms. Is there an answer? 0.845. Questions? No questions? Very easy, right? It's not hard. It's just this. It's just a question. And some of you may have seen this in the past in chemistry. I believe you guys came too. They do this. They use calories in there though. Okay, let's do this one. Let's take a look at this. So it's here an aluminum calorimeter. Okay, so now we have an aluminum like the one that you did, right? The aluminum calorimeter with this mass, it contains this amount of water. So we cannot ignore now the calorimeter. The calorimeter and water, so this is the experiment that you guys did. The calorimeter and water is at 10 degrees Celsius of equilibrium. All right. It says two metallic blocks are placed into water. One is copper. The other one has a mass of this at a temperature of 100. The entire system stabilizes at 20 degrees. Okay. This is a very nice. I was actually thinking about doing this, but it's a little bit too much. And theoretically, it's nice. You can do it. In the lab, it's a mess. You might having two samples, right? So, but let's see. Let's see what should we expect. So we have a calorimeter, right? Like a container like this. And you're gonna have two samples, not just one. So what you have to think is that you have four objects: the calorimeter, water, copper, and the unknown sample. And four values of temperature. The temperature of equilibrium is 20 degrees. Copper is at 80. The other sample is at 100. And the aluminum and the water are at 10. So let's take a look. This is a more interesting one though. So this is your calorimetry experiment. Right? So again, this is why this method is very useful, because now you can identify everything that's happening there. So first we have the water and the aluminum both at 10 degrees Celsius. Now the mass of water is 0.250 and the mass of aluminum is 0.100. So 0.100 for this guy. So 0.1 and 0.250 for water. So quite a bit, basically a very realistic experiment. Then you have a copper, 50 grams at 80. Oh, 50 grams, right? So we have to change that into kilograms. 50 grams is 0.05 or 0.050. And then you have an unknown element, 70 grams, so 0.07 at 100 degrees. That's why I left some space here. That's 100 degrees. You don't know what this is, but you know it's 0.07. And everything reaches equilibrium at 20 degrees Celsius. So about here. All right, so what's your Q gain? Water and aluminum. What's your Q lost? Copper and the unknown sample. So I'm going to be asking questions, all right? Q gain equals to Q lost. All right. So for water, what is the change of temperature of water, guys?
10.
10. So 0.250. If somebody can be helping with the math, please, thank you. All right, that's the mass of water times 4186 times 10. And what's the change of temperature for the calorimeter?
Same thing, 10.
And so 0.100 times what's the specific heat of aluminum?
900.
Yeah, 900 and 10. Okay, you guys have it in front of you. Please, I need somebody to calculate this, all right? And then that's Q gain. Q lost here. So now let's do copper. What's the change on temperature of copper?
$60.
60. So 0.050. Okay, copper. copper, 387. All right. So 387. Specific heat, 60. And then the unknown element. What's the change of temperature for the unknown?
80.
80. So 0.07. The unknown, we don't know, so we want to calculate as C, right? And the change of temperature, 80. Okay, so this is, if you keep it organized, easy. Somebody, what's this value here?
I got so it was 11,305.
7,000.
I got 11,365.
Yeah,
11,000.
same thing. 11,365.
It's 11.
Oh, 11. So 11,365. Like this.
Yeah.
Yeah, this time. Okay, joules. And then this, how much is this?
11,610.
I got
Oh, no, it cannot be that much.
Yeah, I got 1,166.
1,100,
66.6.
like that.
I got 1,161.
Yeah, it should be 1,161.
Like this.
Yep.
Yeah, that's what I got.
And then what's 80 times 0.07? 5.6, right? 5.6 C. 5.6 C. There. So this equals to this. So then we do 11,365 equals to 1,161 plus 5.6, the unknown element. So this 365 minus 1161 divided by 5.6. Ooh, it's a lot. So the unknown element is 1,100 and 1,822. Units, because everything is in joules. Joules per kilogram, I use kilograms, Celsius. So we'll check that. Yeah, exactly. All right, guys. So questions. Any questions that you need to clarify here?
So regarding the masses of the atoms and elements, so are we going to be given those, or do we have to remember them for the exam?
For what? The
Like-
mass?
Yeah, for the masses.
The masses have to be given, unless you have to calculate them.
Okay, so the masses will be given for quizzes and the exam.
Mm-hmm.
Okay.
Any other question? If you keep it organized, you can do it with 2. You can do it with 4 objects or substances. And then, of course, with a table, you can identify what type of elements. So here, yeah, they don't, might be very in the sense that. So the idea with this is exactly what you can do in any experiment. Is I give you a sample, but normally you will know what sample is. It can be aluminum or copper or brass, and then you compare it, right? For example, if I tell you this is a certain element, right? And the specific heat theoretically is 1,800. So you can do a comparison there. Why is not exactly 1,800? Because we are assuming that nothing is lost in the surroundings. Even though now we're more precise. We're considering water and a calorimeter, right? So whenever you're doing an experiment of calorimetry, both are in equilibrium. Let's do something easy with phase change, and then let's do a more interesting problem. Yeah, so look at that one, right? You have certain amount of energy transferred to a certain amount of ice. So this is actually not bad, right? You can estimate how much energy you can give from a boiler, from a radiator to 2 kilograms of ice. And then they ask you to first calculate the energy required to melt all the ice into water. Okay, so if they give you the mass of ice at 0 degrees Celsius, let's find how much energy we need to melt the ice. So, you have 2 kilograms of ice. The energy required to melt ice is Q equals to ML. MLF, latent heat of fusion. All right, that's to melt. This is energy to melt the ice. So LF, what's LF? So we have to go here. 3.33 times 10 to the 5. So let's write that here. So LF is 3.33 times 10 to the 5. Joules per kilogram. So part A, Q will be 2 multiplied by 3.33 times 10 to the power of 5. This is just 6.66 times 10 to the 5 joules. Let's double check. There it is. All right. Now, this is what's interesting. How much energy remains to raise the temperature of the liquid water? So once you melt it, you're going to increase the temperature. So this was the original energy. And this is the energy you use. So how do you find the remaining energy? What do you do? What do you have to do? What do you think?
Sorry, can you repeat the question?
If you have this energy originally, and you already use this to melt ice, how much energy you have remaining?
Just subtract.
Yeah, subtract that minus. So 2.64 times 10 to the 5, 2.64 times 10 to the 5. So that's the energy remaining to raise the temperature of water. So 2.64 times 10 to the 5. So now, let's see part C. They're probably asking you if you can boil it. Yeah, determine the final temperature of water. All right. So you are giving Q. So part C, Q equals to the mass, which never changes because mass, conservation of mass, the specific heat capacity of water, so C of water, times the delta T. But ice was at 0 degrees Celsius. So this energy is equal to 2 kilograms of water now, 4186, and the temperature difference is T final minus T initial, which is 0, basically T. Is that clear? That's how you find T final. Yep. 31.5 degrees Celsius. Let's double check. Yeah, 31.5 degrees Celsius. So T is 31.5, which is the average temperature of a summer day. It's about 90 degrees Fahrenheit. Questions? No questions? You sure? All right, let's look for another one that is a bit more challenging. Look at this. This is a good one. That's actually, if you guys do, maybe some of you will go into physics, I don't know. One experiment, you guys did a calorimetry experiment. We also have the melting ice experiment. We bring ice from the lab, and we ask you guys to use a calorimeter to find the temperature of the mixture. And the idea is to find the latent heat of fusion of ice in water. It's an interesting experiment. It's actually very interesting. So basically you have mass, you have a piece of ice at 0 degrees Celsius, and you're gonna place it in 825 grams of water. It's a lot of water if you think about it. At 25 degrees Celsius, so a room temperature. What's the final temperature of the mixture? So you have to be careful because the ice is an ice cube, so it's solid, right? So it's basically what you guys do in a summer day, right? When you have like water with ice, it melts, right? Well, let's take a look. It's the same idea as calorimetry, but now you are adding phase change. So it's more interesting now. You do your number line again. You place the ice at 0 degrees Celsius and the water at 25 degrees Celsius. The mass of water is 825 grams, which you know is 0.825 kilograms. And the ice is 75 grams, 0.075 kilograms. So this is gonna melt, it's gonna heat up, and it's gonna reach a temperature of equilibrium, T. You wanna find this. All right, guys, how do you draw this? Well, you already have that. How do you draw the melting here? Let me show you this trick. Remember that there is no change on temperature when you are melting? Draw a line like this. This is the phase change. We can call this Q or Q prime if you want. Let's just call it QL. Once it melts, it's gonna warm to T. That's your Q. So this plus this is for the ice. And then for the water, oh, this is water here. For the water, it just cools down to T. So the same idea. Q gain equals to Q lost. But Q gain now is this plus this. So first, let's find the Q to melt ice. Mass of ice times LF. Times this. Plus the Q to go from 0 to T. Mass of ice, the same, because the ice melt, but the mass didn't change. But guys, ice melt into water. This is water now. So I use the specific heat of water in this process. So 4186.
Professor, what's the 33.33? What's that value?
This is the latent heat of fusion for ice.
Okay.
Right? So this is M LF plus MC delta T. Delta T for this process is just T minus 0 T. That's what it is. That's Q gain. All right. Q lost. There. Is the mass of water times a specific heat of water Okay, this is what you have to be careful, guys. What is the change on temperature for water? It's not T minus 25. It's 25 minus T. Because you're going from higher to lower. Okay? There you have it. Okay, so what's this number here?
Two, 4, 9, 7, 5.
Like this?
Yeah.
Okay. That's latent heat of fusion or heat of latent heat, yeah. And now, what's 0.075 times 4186?
314.
So 314 T. And now, what's 0.825 times 4186?
3,453.
3000,
453.
like that. So guess what? Now you have an algebra problem here, right? You have to solve for T. We want to do this. So we write this in here. Like that. plus 314T. Okay, when you distribute, what's 3,453 times 25?
86,336. 336.
86,336, like this, right? Minus 3,453 T. So then this number goes to this side, this number goes to this side, so you have this 314 plus 3,453 all multiplied by temperature equals to this number minus this number. What's 86,336 minus 24,975?
61,361.
All right. And what's this plus this? That's 3,767. Yeah, 3,767. Okay. That's T. That's 61,361. And then we divide. What do you get for T? Does it make sense? What's this divided by this? It's like 20, around 20 degrees? Less, maybe?
16.3.
16.3 degrees Celsius. Let's double check. Well, 16 degrees. This is a good question, guys, huh? Where is it? Here. Half of the question is physics, the other half is math. All right, questions. Come on. I know there are questions about this. Questions, guys, questions.
Wait, I'm confused about how you got the value for QG.
So QG or Q gain is the heat gained by ice. So since now we're including phase change, ice has to melt before it raises its temperature, right? So we first find the latent heat of fusion, which is this, and then we add it with the MC delta T, the heat to change from 0 to the value T that you want to find. So same mass, the mass doesn't change. Now it's water, so 4186 something. So what's important here is that you identify the melting process, which is this, and the heating process, which is this. Anybody else has a question about that?
Yeah, so will the ice always be labeled at 0 degrees Celsius? Like, does that
No.
have anything to
No,
do
no,
with
no.
the
No,
no?
I
So
can give you ice at less. This one was 0, but you have to.
okay, and then you would still use in that case the M times LF. It would still because it says it's ice.
Let me see if I can find. No, that's a good question. Oh, there it is. With this, I will show you with this. But yeah, if ice is at less than 0 degrees, there is an extra process.
Okay.
Yeah, so we're gonna show you that. If ice is normally at 0 degrees, so you just start melting and then you heat up. But you can have ice at less. So if ice is at less, there is an extra process, and yeah, you have to consider that as well.
So basically, we can only use this one if ice is at 0.
Yeah, and they have to tell you that.
Okay. Okay. Thank you.
That's it. I would say besides this, right? Be careful how you write the change on temperatures. I think the graph is very important. You see how this allows you to visualize the problems? All right. Well, let's do one with ice at less degrees Celsius. And it's here actually. How much energy is required to change 40 grams of ice at -10 to steam? Ah, okay. So this one is a very interesting problem. Huh? You're going to do a full double phase change. You're gonna melt it and evaporate it. So you need these two. You're gonna melt it and then you're gonna evaporate it. So you can do the graph as well. I will suggest you to do that because you can see what's going on. Oh, I think I need to change the battery of this. You have ice at -10. But guys, ice is not always ice. It goes to 0. And then here, something happens. There goes to 100. And something happens. With water, right? Something happens. And then you go to... So clearly, the problem, it doesn't tell you that. That's something that you guys should know. This is the two values that I put in there, 0 and 100. That's something that you should know. What is 0 degrees Celsius, guys?
Freezing point,
Yeah, and what's 100 degrees?
the boiling point.
Yeah, so those values you need to know. Because ice is gonna heat up, it's gonna melt. Ay, caramba. It's gonna melt. Then it's going to heat again. Then it's gonna evaporate. Evaporate or evaporate? How do you call? Let's see if that word exists anyway. Yeah, evaporate. So you're going to evaporate water. And then you're gonna heat steam. So you can label here ice, water, liquid, steam. What I will give you in an exam is the specific heat capacity of ice. 2090 joules per kilogram Celsius. And the specific heat of steam is 2100. It's almost like ice. Joules kilogram Celsius. All right, so I'm gonna ask. Let's see your understanding. So, who can tell me what's the equation and the value for the amount of heat to raise the temperature of ice from -10 to 0? Let's start with Q1. Let's call that Q1. So what's Q1? The ice is 40 grams. So you have 0.040 kilograms. All right, so what's the equation for the heat here?
Mass times specific heat of ice times the temperature change, which is 10 degrees.
Yep, so this times this. All right, while I'm doing this, somebody please calculate this. And then the melting. How do I find the heat to melt? What's the question for the phase change here?
Mass times 3.33 times 10 to the 5.
Uh-huh, very good. Three point three three times 10 to the 5. All right. Again, somebody be calculating these values. And then we are already in water. So what's the Q? Let's call it Q2 here. How much heat do you need to raise the temperature of water to 100 degrees now?
It would be the mass times 4,184 times 100.
Times 100, right?
Yeah.
All right. You are already at 100. Now we are gonna evaporate the water. So let's call it QLV. LV is this. So what will be the equation for QLV?
Mass times QLB.
So 0.024 or 0.040, sorry, times 2.26 times 10 to the 6. Now it's all steam. Let's call this Q3. So now you're raising from 100 to 110. So what would be Q3?
Mass times 2,100 times 10.
All right, guys. So let's find all the values. Start with the first one. What was the value of this?
836.
Joules. What's the value of QLF?
13,320.
220?
320.
320. What's Q2?
16,744.
700.
44.
QLV.
90,400.
90,400?
Yep.
Yeah, increasing. And finally, Q3.
840.
All right, guys. So what's all these values if you add them all?
$122,140.
Like that?
Yep.
That is all. Okay, whatever. All right, guys. So that is chapter 11. It's nothing that hard. So obviously, I will say review your web assignment. There are good problems as well in there. Okay. There is a couple like this in exam free, but like I said, I want to use this time if anybody has questions from the previous chapters or the previous topics, or anything related to the class. Next week is the last week, remember? So, anybody? Stop this now.